Zijian for the introduction and okay, start recording. Okay. And thank Professor Zhang for the invitation. It's a great pleasure to give a talk here today. And my topic is causal discovery and its application in transfer learning. So this is a joint work with Professor Xinwei Sun from Fudan University and my advisor, Professor Yizhou Wang. Here is the outline of my talk. So first, I will introduce my recent works on temporal causal discovery. I will begin with a new identifiability result for causal graph of subsampled time series. Based on this, I will develop a conditional independent test and a recovery algorithm to recover the causal graph. Then I will extend causal discovery to dynamic systems driven by stochastic differential equations, introducing the first conditional local independent test procedure. Finally, I will demonstrate how causal discovery can be applied to transfer learning. Okay, let's begin now. So time series data is common in the real world. For example, in neuroscience, the progression of Alzheimer's disease over brain regions is a time series. In artificial intelligence, the agent understands human behavior via videos, and the action sequence in the video is also a time series. For formulation, suppose that we have D time series x1t to xdt, with t ranging from 1 to t. We assume the time series is generated via a full-time causal graph and a structure vector autoregression model. So the causal relationships can be summarized via the summary graph, as shown here, where we have xi point to xj if and only if xit minus 1 is the parent of xjt in the four-time DAG. And our goal here is then to recover the summary graph, given Markovian faithfulness and the self-causation assumptions. To achieve this goal, a major challenge to overcome is the subsampling issue, meaning that the time series may be sampled at a lower rate than the true causal scale. So in other words, we can only observe every k time steps. For example, in AD, we have brain scans every 6 months, but the disease may progress faster than this. Such subsampling can induce latent bias, preventing us from identifying direct causation from mediation effect, as in both cases, we will have an edge from xt to yt plus 2. To overcome this challenge, various attempts has been made. However, none of them achieved general identifiability results. For example, the works of Gong et al. And Tang et al. Assumed a linear non-Gaussian model for identification. Dank et al. And etc. had no parametric assumptions, but they did not establish causal identification. So indeed, encountering such difficulty is no coincidence, as these latent variables has long posed a significant challenge for causal discovery. In this work, we established the first non-parametric identifiability result for subsampled time series. Our departure here is that in the time series, each latent variable has an observed descendant in the future time. So we can use the observed descendant as its proxy variable to adjust for the latent bias. So based on this idea, we propose a proximal hypothesis testing procedure to identify the direct effect from mediation and introduce an efficient algorithm for causal discovery. Moreover, it's worth noting that our analysis can be extended to mixed frequency time series. Here is a comparison between our works and between existing works and our solution. We can see that our method is the only one that can achieve non-parametric identification in both subsampled and mixed frequency data. So in the following, I will introduce the identifiability results. I will first illustrate the idea of identification using the following example. The interest here is to identify whether x point to y, given a mediator M and a confounder S between them. For identification, we know that there are three kinds of passes between xt and yt plus k in the full-time DAG. The first one is xt point to yt plus 1 point to dot 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 point to yt plus k, which only exists if x is the parent of y. The second one is a mediation pass. So xt point to mt plus 1 and mt plus 1 point to yt plus k. And the third one is a confounding pass, where xt minus 1 is a parent of xt and is also the ancestor of yt plus k. So we can block the second and third kind of passes and see whether the first pass exists in order to tell whether x is a parent of y. Under the Markovian and faithfulness assumption, this is then equivalent to test the following hypothesis: whether xt is independent with yt plus k given mt plus 1 and st. So for the general case, the set M will block mediation paths, and the set S will block all confounding passes. These sets can be identified from the mag over the observed variables in the following ways. In this regard, we have x point to y in the summary graph if and only if there are xt point to yt plus k and a bidirected edge between xt and yt in the mag, and most importantly, the hypothesis xt is independent with yt plus k given m and s does not hold. So to test this hypothesis, we first note that xt is observable. Therefore, it reduced to testing whether xt is independent with yt plus k given mt plus y after conditioning on the observable set S. However, a problem is that the mediator mt plus 1 is unobserved. So how can we test the hypothesis in this case? For solution, we propose to use the proxy variable mt plus k of mt plus 1. The proxy variable was first introduced by Kuroki and Pearl in 2014. It is a noisy observation of the latent variable from which we can infer information about the conditional independence relationships. Equipped with the proxy variable for identification, we can show the following theorem, which is our main result. So assume Markovian and faithfulness. Suppose that the condition x is independent y given m and s can be identified for any x and y. Then we have the summary graph is identifiable. Specifically, there is x point to y in the summary graph if and only if there are xt point to yt plus k and xt bidirected yt in the mag, and the non-hypothesis h0 does not hold. So with these identifiability results, what's left is to develop a procedure to test this conditional independence with the proxy variable. We formulate this problem as follows. So the non-hypothesis h0 is x independent with y given some latent variable u. We assume the availability of a proxy variable w of u that satisfies the condition x is independent with w given u. For examples, W can be the child or descendant of U as shown in these figures. As mentioned, the proxy variable was first introduced by Pearl for causal inference. Later, Miao et al. Employed it for hypothesis testing over discrete variables. So to be specific, when X, Y, and W are all discrete and the non-hypothesis hold, they show that they can use the conditional independence between x and w given u to establish a linear equation. Py given x equals to pw given x multiplies a coefficient matrix. Then they propose to test the non-hypothesis by regressing py given x on pw given x. So if the residual c is large, we reject h0 and believe there is a direct causal influence from x to y. However, when it comes to continuous variables, there are two issues for such a process. First, the independence structure, thus the linear equation, may not hold after discretization. Second, one should ensure that the matrix Pwx is invertible or have full row rank to make sure the solution of the linear equation is identifiable. Indeed, we find that naive discretization can result in a biased conclusion. So to overcome these problems, we introduce a hypothesis testing procedure based on discretization. At the core of our procedure lies in finding a discretization bins that establish the identifiability of these linear equations. So to achieve this, we first introduce a completeness condition that can ensure the discretized x and w meet the rank regularity. Namely, we need to assume the conditional distribution Pu given x and Pw given x are complete. That is, the conditional expectation of Gu given x is zero if and only if Gu is zero. So this condition is commonly seen in proximal causal learning and non-parametric instrumental variable. For discrete variables, it degenerates to the rank condition assumed by Mjodl. And it can easily hold for a broad family of models, such as the addictive noise model. So assume this completeness condition, we can show that for any discretization of W, there exists a discretization of X and U, such that these two matrices PW given X and PW given U are invertible. In the paper, we also designed an algorithm to find the corresponding discretization bins of X. After discretizing X, we hope to have the following equations, where EY and EW represent the discretization errors. To control this discretization error, we further impose the smoothness conditions. We need to assume the conditional distribution Py given x is Lipschitz continuous with respect to the total variation distance. Under this condition, we can show that these discretization errors, EY and EW, can be effectively controlled with refined partitioning. So after discretization with these completeness and smoothness conditions, we can estimate the conditional probability matrix of this discretized variable Py given x and Pw given x using maximum likelihood. Then, by regressing Py given x on Pw given x and computing the residual, we can get our testing statistic, T, which equals to n c squared. We show that T converges to a chi-square distribution with degree of freedom R equals to Lx minus Lw. Here the Lx is the levels of x and the Lw is the level of w. So as a result, for any level of significance alpha, we can control the type 1 error below alpha asymptotically. Now, having addressed the proximal hypothesis testing, we can recover the summary graph with the following algorithm. So the first step is to recover the MAG from the observational data using the FCI algorithm and the temporal order. Then, for each pair of vertices x and y in the summary graph, we need to check whether there are xt point to yt plus k and a bidirected edge between xt plus k and yt plus k in the MAG. So if there are such edges, we then identify the conditioning sets M and S and test the non-causal hypothesis using the proxy variable. If the non-hypothesis is rejected, we add the edge x to y to the summary graph. Otherwise, we do nothing. Finally, we return J after all pair of vertices has been checked. Indeed, our identification strategy can be easily extended to mixed frequency time series, where each xi may have a different subsampling factor ki. So for that case, we can let k be the least common multiples of these ki's and apply the above algorithm to the ensembled series. We show that the identifiability result still holds, and the proximal hypothesis testing remains well calibrated. Now we verify our algorithm on synthetic data, where the ground truth causal graph is randomly sampled and the structure functions are picked from common nonlinear functions such as sine and sigmoid. As we can see, our algorithm demonstrates high precision and recall under different settings of subsampling factor and sample sizes, while the baselines fails. Then we apply our method to recover the causal graph of Alzheimer's disease. So in AD, patients suffer from memory loss due to the atrophy of memory-related brain regions, such as the hippocampus and medial temporal lobe. A widely accepted explanation for such atrophy is that the disease may release toxin proteins, such as A beta and tau. These proteins spread from one brain region to another, eventually leading to the atrophy of the whole brain region. Now, the causal graph then characterizes the pathways of such protein spreading. We show the recovered causal graph on the left and combined brain regions in the same cortex on the right. So as we can see, the disease originates from the hippocampus region and gradually spread to other brain regions such as amygdala and the temporal lobe. The topology order is consistent with the atrophy order found in clinical studies, which verifies the effectiveness of our method. Okay, so this concludes the first part of my talk. In the following, I will extend causal discovery to dynamic systems driven by stochastic differential equations. The motivation is as follows. Except for mildly progressed time series such as AD, in the real world, there are also many high-frequency time series. For example, in neuroscience, the interaction between neurons happens at a time scale of milliseconds. The evolution of such systems are usually modeled by stochastic differential equations. For such SDE-driven systems, traditional structure vector autoregression model can fail to represent the causal relationships. Consider the following linear SDE system as an example. We have X1 does not directly influence the evolution of X3 and X4. Hence, intuitively, X1 should not be the direct cause of X3 and X4. However, in the corresponding SVAR model of the discrete observations, we have non-zero elements in X1 t minus 1 to X3 t and S4 t due to the accumulation of causal influence in time. So that means if we use the FAR model, the identified causal relationships may be biased. Moreover, since there are infinite unobserved time steps between any two observations, the proxy variable may be dominated by exogenous noise, thus losing its power due to the failure of the completeness condition. So to overcome these problems, we introduce a notion of local independence, which characterizes causation in dynamic causal models. So specifically, consider the process xt that satisfies the following SDE. We denote ft alpha as a filtration generated by the process x alpha. The filtration contains possible events and information of the process x alpha. Then we set the process x beta is locally independent with x alpha given the filtration ftc for some condition in set C. If the projection of lambda beta to ftc is the same as that to ft alpha union C. So to interpret, we know that for two processes alpha beta, we have x beta is locally independent with x alpha given the rest of the process if lambda beta does not depend on the sample path of x alphas. Local independence can be seen as a continuous time version of the notion of grandeur non-causality. So we know that this definition does not imply lambda beta given fc equals to lambda beta given f alpha union c for any time s and t, hence the name local independence. Furthermore, local independence is asymmetric, which aligns with the symmetry of causality in time. Then, for a given dynamic system, we can define a local independence graph where there is an edge alpha point to beta if and only if alpha is conditional local independent with beta. Under the Markovian condition, the local independence graph represents all conditional local independence relations, therefore characterize the causal interaction of the dynamic system X. Now, our goal is then to recover the graph G, and the key of which is to develop a conditional local independence test. So for brevity, we denote FTC and as FT and denote ft alpha union C as JT. We let mu t and bold mu t to denote the projection process of lambda beta to ft and jt respectively. Now our non-hypothesis then state that mu is a version of bold mu. To design a testing statistic, we first note the following martingale property. Here, an FT martingale is a process MT such that the conditional expectation of MT given Fs equals to Ms. In other words, we cannot predict the future behavior of MT based on information into the time S. An example of martingale is the Brownian motion. So we show that under the certain integrability regularities, we can construct a process MT defined by x beta minus the integral process of mu. This process MT is an FT martingale. And similarly, we can construct a process bold MT by minusing integral of bold mu from x beta. And this bold MT is a GT martingale. So in this regard, under the null hypothesis, we have M equals to bold M is also a JT martingale. Now we can consider the stochastic integral process IT defined by integrating x alpha with respect to MT. We have IT is a martingale process with mean zero. So we can detect H0 by checking the deviation of EIT from the zero process. If we find EIT is not zero, we can reject H0 and claim that there is a causal relationship. In practice, we need to replace the integrand with the residual process GT of x alpha minus pi t for some statistical convenience. We then define the following quantity gamma, which is the expectation of IT as a local covariance measure. We show that under the null hypothesis, the process IT is a GT martingale with initial point 0. Thus, we have gamma is the zero process. Moreover, we can show that gamma is the integral of the covariance between G and the difference between mu and bold mu, which explains its name as the local covariance measure. To estimate gamma, we consider the following sample splitting estimator. So specifically, we split our NIID sample trajectory into two disjoint sets, J and JC. We first estimate pi and mu using data indexed by JC. Then we estimate gamma via discretized summation and sample mean on J. So to show the asymptotic properties of gamma, we need to decompose it into three terms. So U plus R plus H. The process H is zero under the null hypothesis because mu equals to bold mu. And we can use a central limit theorem to show the convergence of the process U and use the consistency of G hat and mu hat to control the residual terms R1, R2, and R3. In details, we have the following theorem under the consistency and bounded moments assumptions. So under the null hypothesis, we have root n multiplies gamma hat converges in distribution to U0 as the sample size n goes to infinity and the observational interval delta goes to 0, where U0 is a mean zero continuous Gaussian martingale with variance function defined by Vt. In practice, we can estimate the variance function where its empirical version, and by assuming the consistency of sigma hat, we can show that V hat is also consistent. We then consider the following testing statistic T, defined by root n multiplies the superior norm of gamma T, and normalized by Vt hat. To establish the asymptotic level of our test, we need to assume the variance is bounded away from 0. Then we can show that the statistic T converges in distribution to a random variable S, where S has a distributional representation as the superior norm of a Brownian motion. We can write the cumulative density of S as follows, from which we can decide the critical value of the test. So in general, we cannot expect our test to have power against all alternatives to H0. This is similar to all other types of conditional independence tests. However, we do have the following results that establish power against alternatives where gamma is non-zero. Moreover, we can improve the efficiency of our test using cross-fitting. So specifically, we can switch the role of G and GC to obtain two estimators, gamma 1 hat and gamma 2 hat. Intuitively, these two estimators are independent. Hence, their average should lead to a more powerful estimator. Such a procedure can then be extended to k-fold cross-fitting. We then define our testing statistic as root n0 multiplies the supreme norm of gamma t k and normalized by v hat t. So notably, the cross-fitting approach recovers full efficiency in the sense that the convergence rate is n0 instead of root n. And we can show that the cross-fitted statistic also converges in distribution to S. Nonetheless, an important question remained unanswered is that how can we estimate the process Wt, pi t, and mu t? So for solution, we know that pi and mu are both projection processes. Hence, their evolution follows the optimal filtering equation, for example, the common filter in the linear case. So for example, in the linear OU model, the process MT, which is a projection of x v minus c on ft, has an evolution characterized by the following SDE, where the parameters at, bt, and dt are determined by the variance process and the model parameter phi. Therefore, we can first estimate the model parameter phi, then use the Euler-Maruyama method with plug-in phi hat to estimate MT. And after that, we can take the alpha's dimension of m hat to be pi hat and estimate mu by the following equation. So in practice, to achieve statistical consistency, we need to truncate the singular values of phi hat. We show that the estimators we construct, mu hat and pi hat, are both consistent. Therefore, the requirements in assumption 1 is satisfied. We now verify our procedure on synthetic data. As we can see, our method can effectively control the type 1 error below the significant level and have high powers. In contrast, the grandeur test and the naive test based on linear regression fails. We then apply our test to recover the dynamic causal graph in brain resting state fMRI. So the result is shown here, where regions in the left and right brains are placed in the left and right respectively. So to interpret this graph, we say that it is symmetric with dominating links in symmetrically located regions and regions in the same subgroup. In particular, we observe that the visual cortex and the sensory motor cortex have high connectivity, which can be related to the activation of visual and sensory function in the resting state fMRI. Besides, we note a connection from the inferior parietal cortex to the inferior frontal cortex and the prefrontal cortex, which are known to be related to working memory. And the connection between the inferior parietal cortex and the temporal cortex can be attributed to the fact that they are both components of the default mode network. Finally, we can observe a clear distinction in causal links among cortical regions and subcortical ones. This phenomenon is also observed in a clinical study. Now, this concludes the second part of my talk. So above, I have talked various causal discovery methods from time series. In the following, I will demonstrate how causal discovery can be applied to design robust machine learning models against distributional shift. We know that a major barrier to deploying current machine learning models lies in their sensitivity to dataset shift, such as covariance shift and label shift. When this shift exists in deployment environment, the model may give unreliable prediction results, which can cause severe consequences in safe-critic tasks such as healthcare. At the heart of this unreliability issue are stability and robustness aspects, which respectively denote the insensibility of prediction behavior and the generalization error to dataset shifts. So given a stable set of predictors, our goal is to find the most robust one, F star, which minimizes the worst case risk. To achieve this goal, various attempts have proposed learning causal features for generalization. For example, the ICP leveraged causal parental information, anchor regression interpret between ordinary least square and a causal minimax least square under linear model assumption. However, this method depends on limited information or impose strong parametric assumptions, constraining their application in the real-world scenarios. So in this work, we present a novel approach that expands the feature considered beyond causal features. Specifically, we first employ the sparse mechanism shift hypothesis and intervention to identify a set of stable predictors. Each corresponds to a subset of the stable set. Then we propose a graph condition for Fs to be optimal. This condition can be verified by causal discovery. When this graph condition is not met, we propose a searching paradigm to identify F star. To reduce the searching cost, we introduce a concept of graph equivalence class. So in the following, I will first introduce the stable predictor set we define. So specifically, we assume the joint distribution Pxy is entailed by DAG G over V for all environments. To build a connection between the training and deployment environments, we adopt the sparse mechanism shift hypothesis, which states that the distribution shift in Pxy is a result of changes in a subset of the causal factors. So we call this set of variables whose causal factor change as mutable vectors. And correspondingly, we call the set of variables whose causal factor keep invariant as the stable set. We assume the causal factor y is invariant, as also adopted by existing works. So to identify the mutable set, we need to assume the following consistent heterogeneity assumption, which states that for every mutable variable, there are existing two different environments in the training set, such that the causal factor of J differs.
Sorry.
To obtain.
Oh, sorry.
Okay.
Can I ask a
So is there a question?
Yes. I want to ask
Okay.
What's the meaning by x and m in the first equation?
What's the meaning of x and m in the equation?
First equation, yes, this slide.
Okay. So S and M are two index sets. Okay. So for every I in S, the causal factor that generates xi from its parent is invariant to all environments. But for all variables in the set M, the factor that generates xj from parent j may be different in different environments. So we call the set M as mutable because its causal mechanism change. And we call the set S as stable because its causal mechanism does not change. So does this answer your question?
Okay, so you mean the xm denotes the variable influenced by domain, right?
Right. XM is pointed by the domain index variable, right?
So, okay, I see.
Okay.
Thank you.
Then I will continue. Okay.
Sure, thank you.
So we're talking about how to obtain stable predictors. So to obtain stable predictors, we need to remove these mutable factors in the joint distribution. So how can we achieve this? For a solution, we consider intervention on XM. This intervention removes the mutable generation mechanism of XM, thus resulting in a stable interventional distribution. We show that for each stable subset S prime, the distribution PYXS prime given dual XM is invariant to distributional shift. So from this conclusion, we can define a set of stable predictors. Each corresponds to a subset of the whole stable set. Then finding the optimal predictor F star is equivalent to identifying the optimal set S star. To identify the optimal subset, we first introduce a graph condition under which we can directly have S star is S, that is the whole stable set. So specifically, we let xm0 be the mutable variables in Y's children, and we let W as the descendant of xm0. Then we show that we have X star is S if Y does not point to any vertex in W. So for illustration, consider the following two causal graphs as an examples, where the set xm0 is xm and the set W is x1. So in figure 1, we have Y does not point to x1, so the optimal set is the whole stable set. To understand this graph condition, we know that it holds if and only if the interventional distribution can degenerate to a conditional distribution without the do. This degeneration allows us to construct a distribution PE, where any predictor can have a larger quadratic loss than Fs, hence showing the optimality of SS. So for example, in figure A, where x2 blocks y from x1 and xn in the intervened graph, the interventional distribution Py given x1, x2, and do xn can degenerate to the conditional distribution Py given x2 using the first rule of do calculus. In contrast, for figure B, where y point to x1, here the x1 becomes a collider and prevent us from removing the do. Indeed, the graph condition can be verified via causal discovery. So we show that under the Markovian faithfulness and consistent heterogeneity assumptions, we have the set W is identifiable, and the condition Y does not point to W is testable. In practice, we can adopt the following procedure for verification. So first, we recover the skeleton and rotation of the graph. Then we use the domain index variable E to detect the mutable set. So for each mutable variable, we can use the weight structure and the Hilbert-Schmidt independence criterion to determine its children and parents. Then, in a recursive manner, we can decide the descendant of xm0, thus identify the set W. So then we can just see whether X point to any vertex in the set W. If there is no such edge, we have the condition holds and the whole stable set is optimal. So on the other hand, if we find Y point to W, the set S may not be optimal. We can construct a counterexample where the worst case risk of the whole set is larger than that of the ampli set. So how can we identify the optimal set S star in this case? For solution, we propose a learning-based method to estimate the worst-case risk of each predictor. To be specific, we consider the instrumental distribution pH obtained by do xm to hpam. So this distribution keeps the invariant mechanism unchanged while allow xm to change arbitrarily given its parents. Therefore, we can optimize H to mimic the worst-case environment and estimate the maximal population loss. For implementation, we parameterize H with neural network H theta and optimize over theta. We can show that for each subset S prime of the stable set, the maximal population loss obtained by optimizing H is the same as the worst case risk. So in that sense, we can estimate the worst case risk of each predictor and choose the optimal one via comparison. So here is our algorithm. We first determine whether the graph condition holds. So if it holds, we just return S as the optimal set. Otherwise, we need to search over every subset and compare their worst case error. So indeed, this strategy needs to search all subsets of the stable sets. So one may ask, is there a more efficient strategy? Fortunately, the answer is yes. We find that among these stable subsets, there are many equivalent ones. So to characterize this phenomenon, we introduce the following notion of graph equivalent relation. So specifically for two stable sets, S1 and S2, we call their equivalent if there is an intersection set, S-intersect, such that this set blocks Y from the rest of elements in S1 and X2 in the graph. So for example, in this graph, we have X1 blocks X2 from Y. Therefore, the set X1 is equivalent to the set x1 and x2. So we call elements of the quotient space as the equivalent classes, and we use bracket S1 to denote the equivalent class of x1. So under the Markovian and phase one is conclusion, we can conclude that if two sets S1 and S2 are equivalent, then their predictors are also equivalent. So here is our algorithm implemented with the equivalent class. When the graph condition fails, we just need to search over all equivalent classes. So in the paper, we show that this can actually reduce the computation cost from NP to P when the causal graph is sparse. We also have a algorithm that can recover the equivalent class. I will just skip here for the time limit. Okay, so with this algorithm, we can now verify our method on synthetic data. So as we can see, when the graph condition holds, the whole stable set is indeed optimal. When the condition does not hold, we can see that the worst case risk estimated by our procedure is consistent with the true risk, while the validation loss adopted by baseline methods can fail. Finally, we can see that the searching cost over equivalent classes is significantly lower than exhaustive search, especially when the graph is sparse. We then apply our method to the prediction of functional activity questionnaire score in AD. So the FAQ score is an important metric to evaluate the cognitive level of AD patient in clinic. We will show the recovered causal graph here, where the multiple regions, hippocampus, pallidum, and caudate are marked in red. So we can see that FAQ points to hippocampus and the medial temporal lobe. Therefore, the graph condition is not met. Hence, we need to search over all equivalent classes to compare and decide the optimal predictor. As we can see, our predictor outperforms all baselines in terms of stability and robustness. Okay, so this finished the final part of my talk. For conclusion, we first study causal discovery from subsample time series. To overcome the mediation bias, we introduce a proxy variable for adjustment. Our analysis can be extended to mixed frequency scenarios. Then we extend causal discovery to high frequency time series via the notion of local independence. So for testing, we introduce a statistic via stochastic integration. We show that the statistic is zero under the hypothesis of no causality and establish the control of type 1 error. So finally, we demonstrate the application of causal discovery to transfer learning. We introduce a set of invariant predictors via intervention, and we show that the most robust one can be identified via causal discovery. So in the future, I'm interested in exploring causal discovery from a single sample trajectory. I plan to investigate mixing types conditions such as alpha mixing, as well as text for martingale different hypotheses for realization. Then I plan to apply dynamic causal discovery to the deformable object manipulation task in embodied AI, such as close folding. So in this task, the causal graph can provide a sparse representation of the dynamics of the object, thus enhancing the efficiency of the manipulation algorithm. So another area I wish to explore is causal transfer learning in policymaking. So here is a transfer learning environment benchmark we developed called the causal escape. So in this environment, the agent is tasked to explore these causal rules in order to escape this room. For example, he needs to check the table and he needs to open the cabinet to find the key and use the key to open the door. So different rooms may share common causal structures, provide the possibility of efficient policy transfer. Okay, so here is my references, and that will be all. Thank you for the listening.
Any questions for Mitchell? Yes. Okay, I have one question. Can you move to the slide about the distant frequency time series?
Okay.
Yes. I want to know. Okay.
Okay, you can see. I can hear you. Okay.
Yeah, I want to know the
here.
relation. Yes. Yes. First, I want to know the relationship about the subsample time series and the base. this frequency time series, can you consider the time step without sampling as the missing value or the length variable in these cases?
Sorry, I didn't hear your last sentence.
Okay. I mean, did you consider the time step that are not sampled as the missing variable
Right,
are the
right,
mental variable?
right. The time steps that are not sampled are latent variables, right?
So how can you extend it the Peel's work to the least frequency time series? Because in my opinion, you do not consider any length variable in your Peel's work.
Sorry, I didn't consider sorry, what variable in my previous work? Any proxy variable?
Length variable in your Peel's work.
Instrumental variable, right?
Length variable. Yes.
Latent variable.
Length variable.
Latent variable.
Oh, latent variable. Okay, okay. So I didn't consider any latent variable in my previous work.
Yes, the subsample time series data. The work for subsample.
Oh, so in the subsample time series data, the subsample variables are latent variables, right?
Subsample variable and length variable.
Right. You see for the we can see this example. So here. So for example, the subsampling factor is k, right? So we can observe values at time t and time t plus k, and all variables between these two time steps are subsampled. Therefore, we consider them as latent variables. Okay. So in the mixed frequency, okay, so it's we can just use the largest subsampling factor. So for example, in this sequence, we can consider this time step and this time step as sampled variable, and all steps between them as subsampled one, and apply our procedure, right?
Okay, I see. I got it. Thank you very much. Any other questions?
Yeah, actually, I have a very similar question to the Jeff's question. So please go back to your first part work. Is that okay? So that's the hypothesis testing with unobserved mediators. So
This
I
one?
guess you model. Yes, I guess you model the mediator as the unobserved variable, right? And
Right,
you
right.
assume that, and you assume that the mt plus k is observed.
Right.
As the okay, so why mt is not observed, but mt plus k is observed?
Oh, MT is also observed, but it cannot be used as a proxy of MT plus one.
Why can't we just use the mt instead of mt plus k? Because all of them are observed in your case. Yeah.
Okay, so if I understand your question, so for example, we have MT here, right? So MT point to MT plus one. MT plus one is a latent variable, right? So in this graph, it would be W point to U and U point to Y, right? So under these graphs, these conditions, X is independent of W given U will not hold anymore. Because sorry, let me think. So for the mediation case, right? So W point to U and U is pointed by X. So U is a collider. So between W and X, right? So if we condition on U, this conditional independence will not hold. And our testing procedure actually relies on these conditional independence properties. So we cannot use MT as the proxy variable of MT plus one. We must use MT plus K, right?
Okay. Yeah, and another question. I'm not very familiar with MAG, but you mentioned that maybe in your 11th slide, number 11.
Okay. Here,
yeah,
right? Here.
No, I think it's the hypothesis testing with unobserved mediators. Yeah,
Okay.
this one. So you
Okay.
mentioned that if there are xt and YT, there's a bidirection edge in the mag. Could you please illustrate on the how will this case be happening?
Okay.
Why there's a, yeah.
I get it. Okay, so I can use this graph, right? Here is a mag, right?
Okay.
So we can see if x point to y, right? So if x point to y, this variable xt plus k minus 1 would be the parent of xt plus k, and simultaneously the parent of yt plus k, right? So there's a latent confounder between xt plus k and yt plus k. Therefore, there is a bidirected edge between xt plus k and yt plus k. There is a bidirected edge between xt and yt. So because the latent confounder is xt minus 1.
Okay, so thank you for your explanation.
Okay.
I have a follow-up question with Jen's question. So can you go to the page that multi-frequency where you have more?
Sorry, the page of frequency.
Multi-frequency. Mixed frequency.
Oh, okay. So still this page, right? Mixed frequency.
Yes. I have a
Okay.
follow-up question. So if I understand correctly, it will basically mean that if we meet mixed frequency time series, we just choose the largest time control one. Is that what
Right.
Then in that case, how can you tell the difference between figure A and figure B? Because if we choose within this criteria, actually we cannot tell the difference between A and B.
Sorry, I didn't hear your last sentence. The signal is a little bit right.
So,
Can you like
if we just choose the largest time sample rate, yes, then how can we tell the difference between case A and case B?
Okay, well, we can't. We can only recover the summary graph, right? So we can't know information about the fall time DAG, right?
So you cannot identify the time delay causal relationship in these cases, right?
Sorry, can you like repeat a little bit?
Sorry, since you can only identify the summary graph, right? So and we cannot identify the time delay causal relationships.
Well, so we assume there's only a time delayed causal relationship you see in this fall time DAG. So here, you mean by time delayed causal relationship, you mean the edge like xt point to yt plus k like this?
Yes.
Okay. Actually, we can identify the summary graph, and if we know the subsampling factor k, we can identify the time lagged details. But if we don't know the k, we can identify these details. Right.
I see.
Right, because okay.
Go ahead.
You go ahead. Okay.
Okay. I mean that if the time series contain the time delay causal relationships and the instantaneous causal relationships, right? And
okay, actually, we assume there is no instantaneous relationship. So we actually need to forbid there's an edge between xt to mt because we kind of assume this causal relationship happens. So in some time, so there can be a cause between two variables at the same time, right?
I see. Thank you very much.
Right. So if you want to like model instantaneous effect, we just need to consider this local independence framework, right? So in these high frequency scenarios, most of this effect would be instantaneous one, right?
Yeah, I agree with you.
Right.
Okay, thank you. Thank you, John. Today, since we have another meeting in 3 minutes, we can stop now. Yes, that's
okay.
Yes, let's continue again.
Thank you for listening. Thank you.
So.